Welcome to this presentation on the bolt type of connectors. My name is Mike Fiedler and I'm a designated support specialist at Autodesk, and I'm going to walk through this topic with you today. So let's go ahead over to Inventor and take a look at the geometry that we will be working with today. Here we are inside of Inventor with the assembly that we have been using parts of in order to investigate various topics and applications within our study of finite element analysis. Today we are talking about bolts, so I'm going to zoom in on this area of the assembly, this fender assembly, and I've already opened up that sub-assembly. You can see I've named this model Fender Assembly 1, and it has CAD models of bolts and nuts in there. So I will upload this into the data sets of the learning content so you can pull this model down and work with it if you'd like. I am also uploading Fender Assembly 2, where I have removed the CAD versions, because the CAD versions of the bolts, that is, because we are going to replace them with the idealizations that are available within Nastran. So we will take a look at how to do that here very shortly. Before we go into the Nastran environment, I just do want to note that inside Inventor, if you go over to the Design tab, there is a bolted connection module here, and this can help you to determine how many bolts you need. It can help you determine things like preloads that you would need. So I'm not going to focus on that too much for our particular walkthrough. We're going to stay focused on the FEA end of things, but certainly you might want to take a look for any sorts of tutorial or documentation on the bolted connection utility within Inventor if that is of interest. So let's go ahead over to the finite element analysis environment. So I'm going to go environments, and then from there I can go into Autodesk Inventor Nastran. And when I come into the Inventor Nastran, you see that we have two different materials available, and that's bringing it in from the CAD model. And a portion of this model is defined currently as mild steel, and a portion is defined as silicone. So let's go ahead and generate the mesh. It will become very apparent there. You can see that this has two different colors associated with it. There's a pinkish color for idealization 1 and a green color for idealization 2. So the reason I'm meshing the model is because that will become very apparent which parts are which material. And I see here that we have a meshing failed. Notice that's okay. Let me go ahead and say okay to that. That's going to happen twice. So there we go. With our meshing done, we can see that what would be the flat part here is currently defined as a silicone, and then everything else in our geometry is currently a mild steel. And if we rotate the geometry around, you can see there are two parts which failed the initial meshing. And this is really related to the size of the mesh that we chose. It's just a little bit too coarse for this geometry. So we're going to go ahead and make it a little bit more fine. So I'm going to select mesh settings, and you can see the element size that we did use was a 2.2 initially inches. I'm going to go ahead and set that to 1, and we'll generate the mesh again. So it'll just go through the various parts of our assembly. There we go. We can see that one of the parts that had a problem before is now meshed. Okay, so that was successful, and you can see as a result of that I have 56,757 nodes, 27,000 elements. Not a terrible number of elements, but certainly had we included all the bolts and the nuts in there. Keep in mind that those elements as CAD models require a lot of elements, a lot of mesh. So who knows, we could have had maybe double the number of elements at this mesh size if we had included them. So we're going to use the connectors in order to replace those. So before I do that though, I do want to change, I'm going to make a material change here. So this, somebody had assigned a silicone material, a flap on this fender, and that kind of gets into a different realm. We could consider it non-linear. if we wanted to model that material's behavior appropriately. And so I'm going to go ahead and make a change. We're just going to make it an aluminum material. And you can see here how to change the materials, so that's good as well. If you've never done that, just right click on the material for that idealization. We could type in our properties, or I can say select material, and I can choose from the Autodesk material library, from the Inventor material library, or if I say load database, that should browse into the Nastran library, and I can open up that, and there are the Nastran materials broken out by their different categories: steel and nickel alloy, aluminum alloys, etc. So I'm going to select one of the aluminum. Let's go down and take something like a 6000 series. How about a 6061? Let's do that, and we'll say OK. So that brings in the modulus, elasticity, Poissons, etc. So it now has the material properties for the aluminum, and again, if I expand, you can see it's now changed. Okay, so the other thing that, or one of the next things that we need to do, or our primary focus really, is on the connectors, and specifically the bolts. So let me show you where that is. If we go across the top panel, there is connectors, and we have explored these other connector types. So bolt is the last one remaining that we need to examine. So when I change it to bolt, you can see a couple different things here. First of all, there's next previous, and we'll get to that in just a moment. If I'm just going to start adding the bolts on, you can see it's asking me for a bearing surface or edge for the bolt head. So let me rotate this model around just a little bit and pan it over this way so I can see one of those edges. And I'll zoom in right here. Okay, so I can select an edge just like that, and you see it fills in that dialog box. And then I'm going to rotate my model around a little bit this way and zoom in here. The next thing it's asking for is a bearing surface or edge for the nut. So we'll go ahead and select that, and boom, it puts in the bolt for me. So that creates an element down through the center, a beam element down through the center. It visualizes as a bolt, right? But what it's doing is really putting a beam element down through the center of that hole, and then making a couple connections around the perimeter to the CAD solid models mesh. So it's creating a lot fewer elements than had we actually modeled a physical bolt in there. Okay, and then you can see that it's determining the bolt diameter there, what it needs based on the diameter of the edge that I took. And then below that we can define a washer for the head and a washer for the nut if you'd like. Let me just go ahead and type one of those in just so you can see what that looks like. As I type in that value, you can see that it adds the washer in there. So you could certainly include washers on both the head side and the nut side. Before I get too far into the rest of this screen, I should mention, let me back up for just a moment here. It did say that we can use a bearing surface or an edge. So yes, by selecting the edges there, it is able to determine what's the starting point and what's the ending point, and then place a head on there and a nut on there. But recommended practice would be, if you want to get more detailed with it, what we could have done is split this surface so that we had another surface region around that hole that would define the area that is covered by the head of the bolt, or the area, circular annular volume or annular area that the nut would cover. So if you want to go to that length, you can certainly do that. Again, just I would select this part, draw a circle around that hole, make it whatever diameter the head of the bolt is, or the nuts of the bolt, and then split the surface. And that way you can just select those regions and continue to set that up. Alternative to the bolt is the cap screw. So if I choose cap screw, you can see here that it's looking for similar things. Has the bearing surface for the hex head cap screw, that is where the head of the cap screw touches. It has the diameter still. However, it got rid of the nut items, right? The cap screw doesn't have a nut, it just threads into, kind of like the schematic is showing there, it just threads into something. And so that's why this field changed as well. It's looking for the surfaces for a threaded region. So I would go inside that hole that the cap screw goes into, and I could select that surface where the threads are in contact, so it knows then what the length of that cap screw is. And I do get to define a washer height with the cap screw if I want. And then there's the useful length of the threads. So with a cap screw, of course, you're going to have some region which is the shank of the cap screw, and then you can define what the useful length of the cap screw is. And if you don't fill that in, it's going to use one half of the diameter as far as the definition of it. So, you know, if you are using cap screw and the useful length of your cap screw is longer than that, then certainly you'd want to type in a value there to help define that. Let me switch back to a bolt real quick. Proceeding on with the things that we can define. In here, inside the connector itself, I could say that it's a user-defined material. Click that checkbox. I could define my modulus of elasticity, Poisson's ratio, my thermal coefficient of expansion. Or, since I'm already leveraging two materials in my setup here, you notice that it's able to access either one of those materials. So we'll leave it at a mild steel. And then lastly, on the right hand side are your preloads. So you can either define that in terms of an axial preload, you know, pounds force in the English inch unit system, or in terms of torque, where you define a preload in inch pounds force and the torque coefficient. So either way, you can do that. I'm going to go ahead and define a 50-pound force axial preload, just so we have some preload there. But anyway, our model's not done, right? I have several more holes to go through here. So when I want to add the next one in, coming all the way back to the beginning of the menu, that's this guy right here, this button that says next. So I can just click that, and you see I'm working on bolt number 2. Again, I select the edge, rotate my geometry around a bit, zoom in, and select that. So there's my second bolt. And now I'm just going to go ahead and proceed to do the remainder of those, and I'll be back with you in just a few seconds. Okay, so here I am. That wasn't too bad. I got my 5 bolts in there so that the bolts are now connecting the steel portion of my fender to, really the bolts go through the flap, which is now an aluminum flap, to this reinforcing bar here, and all that is connected via the bolts. So let's go ahead and say OK to that. There's that. And then I need to have some sorts of constraints and load. So we're going to examine it. Let's say that we hit something with the flap. It probably would have been better to have it as a rubber material in that situation, but let's imagine that we did do the aluminum one, and we're going to apply some force at the base here. And then as far as my constraints, I'm going to fix the 2 circular ends of these tubes here where it would attach to the rest of the assembly. Of course, the assembly itself is much more rigid than the portion of the geometry that we're working with here. So it's fair to say that, you know, it's basically fixed at these locations. Let's give that a name. Fixed constraint. We'll say OK. So there's that. There's my fixed constraints. And then we need our load. So I'm going to take the bottom edge of this flap, and we'll select that edge right there, and that's where I'm going to apply my force. And let's just looking at the mini axis, we're going to go in the minus X direction. So let's make that minus 50 pounds force. We'll say OK. Alright, so there's one more thing that we need to do. Because this is an assembly, I need to have my contacts. The program needs to know, how does one part interact with the other parts in the assembly. So for that, I'm going to go with manual contacts. Let's go ahead and, whoops, excuse me. I could go with manual contacts. If I go manual contacts, then of course I'm going to select, a surface and its mating surface and so on and so forth. Great to do to modify or maybe to add a couple in if the need is there. But I'm going to go with auto and let the program automatically scan through here and determine where all the mating surfaces are. Okay, so if I expand surface contacts and I select one of the contacts there, so there you can see that's between the bar that connects this fender to the rest of the assembly and this curved portion of or curved component of our fender. The default type of contact there, if I edit it, our default type of contact is going to be bonded. So that means those two parts are fixed to one another, and I'm completely okay with that. Let's move on down the list. There we can see those two sheet metal parts, and they're going to be bonded. That's fine. What I'm ultimately looking for is where is the contact pair between the fender and the flap, and then between the flap and this reinforcing bar here, right? I don't want those to be bonded, because if they were bonded, what would be the purpose of having the bolts in here, right? I really want the bolts to be what's holding these three different components together. If I were to do bonded, then there wouldn't be any sense in me putting the bolts in the first place. So granted, I'll give you that in a real world scenario. If I were doing this analysis in a more macro level, yeah, I probably would just bond it, because we're probably not too worried about this connection. But the whole point of this particular video is to show you how to do the bolt connections, so so it is. But anyway, we do want that to be surface contact, so let's keep scrolling down until we see where those contact pairs are. And there's one of them there. You can see it highlights in blue that surface of the steel portion of the fender, and then the back surface of the aluminum flap. So let's edit that one, and we're going to change our contact to something that allows it to slide or pull apart. That would be the separation contact. We'll say OK to that. And then again, coming down the list here, right there, contact number 7, that one is going to get changed to. Edit that, and that's going to be separation contact. So that's all of them. The rest are going to be bonded, and then the flap is going to be in surface contact with the steel portion of the fender, and the flap is going to be in surface contact with the steel portion of this reinforcing bar. So really what's holding them all together would be the bolt connectors that we added in there. Okay, and at that point we are ready to execute the analysis, just about. Good thing I thought of it just before we hit the go button. Because we are doing these bolts, there is a potential that we can, I shouldn't say there's a potential, the program can output the axial force in those elements. It can output the shear force, the torsion, those sorts of results. But in order to do so, we need to tell the program that we would like them calculated and output. So the way we do that, go up to where it says Analysis 1, right click and say Edit, and then I need to turn on the output of force and say OK. Alright, at that point we are ready to execute our analysis. So I'm going to go ahead and say Run, and then I will come back as soon as the analysis has completed. Okay, so our analysis just completed. On my laptop, that was about a 7 or so minute analysis, I believe. We made that about as tricky as we could. If you really think about it, we put the load directly onto the flap. And let's take a look at the displacements here. I'm going to expand upon that in just a moment. We put the load directly on the flap, right? And the results here hopefully show that our flap doesn't go flying off into space, which it doesn't. We can see the maximum displacement for this model is 0.144 inches, so a little more than a tenth of an inch, almost 2/10 of an inch, between 1 and 2/10. But you know, happy to see that it all remained connected there, right? Because the flap was in surface contact with the steel portion of the fender, and then it's in surface contact with this bar, and then so we had that to contend with to iterate and make sure it didn't pass through, allow it to slide if it's going to do that, and then the bolts are really what's capturing it all together. But if you think about it, the bolt is connected to the steel side of the fender, and then to the front side or steel portion of the reinforcing bar here. So you know, it took a lot of iterations in order for that to converge and make sure that everything was working well, and we can see that from the displacement output that it was. So everything stays connected. That's good. The bolts did their job, and good to see. So one of the things, I guess a couple things that we want to talk about here, besides just looking at the displacements, of course, we can look at our other types of results that we have here. So we could take a look at stresses. And when I go to stresses, we can go into things like, how about the von Mises stress? I didn't want the bar one, technically. I wanted the element ones for the solids. So let's take a look at solid von Mises. Make sure that we have stresses that are transferring from, again, we put the force on the flap here, and we need to have that load transfer through our bolts and into the remainder of the structure, which you can see that it does, right? So right there on the corners of our steel fender. So it is transmitting the load from one part to the next. That's good to see. So to take a look at the forces within the bolts and some of the other options that are specific to the bolt, we can go to the pull down menu, and then we are going to go into the options under beam diagram. Keep in mind that that connector, the bolt connector, is really just a beam that runs down the axis or the center of our part, or the hole, and you can see that there when we zoom in. So then you can access the different results related to the bolts. So your beam force end AX is your axial force, and then what else might you want to see? If you look at AY plane 1, this would be the shear force in the local Y direction. AZ plane 2 would be shear force in the local Z direction. And then the beam moment end AX is the torsion in the bolt due to rotation. And that all this information will be in the slide content for this particular learning. So please reference that table there if you need to review any of those results. So before we end, I think what I'll do is just return back to the setup environment and just show what the other one looks like, and that would be the cap screw as opposed to the bolt itself. We talked about it a little bit. We kind of looked at the differences in the screen options, but let's change this to cap screw. And you notice when I do that, right, we just get the head of the bolts there, and then as I rotate around here, there we go. The nut end is really gone. It just comes down to where I terminated with the selecting of the edge there. So I could really get rid of that if I wanted to. That was on bolt number 5, right? And so what I would do is, this is the surface for the threaded region. Let's say that the hex head cap screw comes through the aluminum flap and it only threads into this region right here. So when I select that, you notice that that region is now blue, so it knows that's where the threaded region of this hex head cap screw is, or cap screw. So that would be probably a little more appropriate way to define that. And again, of course, I could define what the useful length is there, whether it is in fact 1/2 of the diameter or something different. So you still have your axial preload or torque preload that you can do with the cap screws as well. So it just depends on which type of threaded connector you need for your particular setup. So I think that about does it for this particular video. Thanks for watching.